Hi guys, hopefully you've had an opportunity to work through exam 3 review. I want to go ahead and go through it with you now. And again, hopefully you've looked at it already. If not, please do so before you watch this. All right, so the first question here, explain the role of the mean value theorem in the development of the integral that gives the arc length along the curve f of x. Well, I'm not going to completely, welcome here. All right. So just to remember the context here, we have some curve. And I've got a couple of x values. I have an interval. And I want to know the length of that curve from A to B. And so what we did was, in true Riemann sum fashion, we partitioned this x-axis from A to B. And then we looked at each subinterval. And to get the length, right, let's just say that, I don't know, I'm going to zoom in on one of these. And so it would look something like, maybe like this. And I'm on, I don't know, some interval. This might be xk. This might be xk plus 1. And then what we used for the, let me see here, what we used to estimate the, sorry, let me get my pen. What we used as an estimate for the arc length was the length of that line segment, right? And then we noticed that, right, that had coordinates come back. Xk plus 1, f of xk plus 1. And then up here, xk, f of xk. And then our arc length was approximated by that line segment, right? The length of that line segment, just using the distance formula. And so we had the square root of xk plus 1 minus xk squared plus this guy, right? And then we recognize that this term here was just delta x. And then, and I'm not going to recreate it because I literally did it in the lecture, but here is where we use the mean value theorem, right? We could find some xk star, right? That xk star is somewhere in this interval. If I'm eyeballing it, it might be like right there. Where we have this ratio. And so you might think about what that does to the square root when you make the appropriate substitution, okay? So right here, this piece, we saw the use of the mean value theorem. All right, let's take a look at the next one. All right, so we know that arc length is going to be the integral from 1 to 8 square root 1 plus f prime of x squared dx. So let's get our hands on f prime of x. Well, let's see, 4/3 times 3/4. That's 1. So we're going to have x to the 1/3. And then we have 2/3 times 3/8. So that will be what? 1/4 minus 1/4 x to the negative 1/3. Okay. And plus 5, which is just going to differentiate to 0. And so while we're at it here, let's go ahead and get a common denominator. So x to the 2/3 minus 1. Actually, I'm sorry, 4x to the 2/3 minus 1 all over 4x to the 1/3. Okay. And so my integral becomes 1 plus 4x to the 2/3 minus 1 over 4x to the 1/3, all that squared dx. Okay. And then I've got it set up here. Let's keep it going. So let's see. This is going to be 1 plus 4x to the 2/3 minus 1 quantity squared all over 16x to the 2/3 dx. And then we'll get a common denominator again, 16x to the 2/3 plus 4x to the 2/3 minus 1 quantity squared all over 16x to the 2/3 dx. And then let's just keep going, see where this takes us. All righty. And as always, if you haven't done it, pause it at this point and go ahead and see where it takes you, okay? All right, so I've obviously paused it and went ahead and worked this out. So when you square this, you get this guy. Notice that you've got this thing that's quadratic in x to the 2/3. And so you do some factoring, and then good things happen. And you wind up with 169 over 8. All right. All right, let's take a look at the next problem. Surface area generated by revolving y equals 2x minus x squared, all in the square root, on that interval about the x-axis. All right, so we know that, where to go? Surface area is going to be given by this formula. And then f of x, so square root 2x minus x squared. Then, whoops, the square root of 1 plus, and then dy dx squared dx. So let's find that y prime, okay? I've started, let's do this over here. So y prime, right, will be 1/2 2x minus x squared to the negative 1/2 times 2 minus 2x, which equals after some cleaning up, this, okay? And so my integral is going to become 2 pi (0.5 to 1.5) square root 2x minus x squared. And then I've actually taken the liberty of simplifying this second square root. So this second square root just winds up being, let's see, where did it go? Oh yeah, 1 over 2x minus x squared dx, which means something kind of nice happens. Right, you've essentially got a square root 2x minus x squared times 1 over and the square root 2x minus x squared dx. So those are gone, and we're left with two pi integral from 0.5 to 1.5 of just dx. So we'll have 2 pi x which is 2 pi 1.5 minus 0.5, which is simply 2 pi. Okay, it's always nice when something looks kind of gross or might be uploaded or front-ended with a bunch of algebra, factoring stuff, comes out kind of nice. So I like it. I'll take it. On to the next. Particle is traveling along the ellipse. 4x squared plus 9y squared equals 36. We want to parameterize the particle's motion such that its position at time 0 is 0, 2. Its direction of motion is clockwise and returns to its original position at time t equals 2 pi. So let's think about what this ellipse might actually look like. And if you recall, we're going to get that form just by getting it in standard form for an ellipse, right? So I've got x squared over 9 plus y squared over 4 equals 1. So here's what I want. So here's my ellipse. And here's the point 0, 2. I want this to be time 0. I also want my direction of motion to be clockwise. Now, 2 pi needs to take 2 pi to get around here. So if you think about some of the problems you've seen, a common parameterization is to let x be, like, say, 3 cosine and y be 2 sine. But that would put us in the wrong spot. I want to start at 0, 2. which means I want at time 0 my x coordinate to be 0 and my y coordinate to be 2. So if I let x be 3 sine t and y be 2 cosine t, then what happens at t equals 0? Well, at t equals 0, my x is 0 and my y is 2. So very good. Now, what direction of motion? Well, let's think about this. As t increases, sine, right, is going to increase. So x is going to increase, and my cosines are going to decrease. So my y's are going to decrease. So sure enough, this thing is going to go down and right as I let t increase. And since I don't have any, right, these are just 1t's, I know that my period one time around is 2 pi. So this parameterization is going to work. All right, B. At what values of t is the slope of the tangent line to the ellipse 2/3? So if you think about this, 1, 2, 1, 2, 3, 2, 3. I guess I could have used Desmos, but you know, I just want to show that I'm just this mediocre of a drawer, and that's giving myself credit. All right, so slope 2/3 tangent line. So the slope will be positive, and so it's going to have to be somewhere quadrant 2 and then quadrant 4. Okay, so it looks like we should have 2 places where this occurs. And right, dy dx is actually dy dt over dx dt. And we want to set this equal to 2/3. So dy dt, well, remember that a y was 2 cosine, so dy dt will be negative 2 sine t. And then my dx dt, x, right, again, just pop up here, x was 3 sine, so my dx dt will be 3 cosine. And so we have negative 2 sine t over 3 cosine t equals 2/3. Gosh, that sure looks like a negative 2/3 tangent t equals 2/3, or tangent t equals negative 1. Well, where does that happen? Well, quadrant 2, 3 pi/4, and quadrant 4, 7 pi/4. Okay. All right, let's do our last problem here. And we saw one similar to this in lecture where we found the area, I think it was inside the circle, but outside the cardioid. Well, now we want to go outside the circle and inside the cardioid. So that's going to be all this. Okay? And so my bounds will be here and here. Okay? So let's think about what these would be, right? If this is theta equals 0, right? This is 1, 0. This point up here is going to be 1 pi halves, and this point down here is going to be negative 1, 3 pi halves. And then from pi halves to 3 pi halves, which is the greater value, which has a larger r value? Well, the cardioid, right? And so that area of this polar region will be from pi halves to 3 pi halves, 1 minus cosine theta minus 1 d theta. Sorry, I meant to write the formula first. I'm going to square this. You know what? I'm sorry. I'm going to scoot this over just a little bit. Give myself a little bit more room. So let me scoot it over just a little bit. Sorry about that. Okay. So area, and then pi halves, 3 pi halves. And so like I said, that outer area is cardioid, right? And the inner area is, or radius is the circle. And then you have 1/2 and d theta. And at this point, we're just kind of chugging along. So let's see, what are we going to get? 1 minus 2 cosine theta plus cosine squared theta minus 1 d theta. So if I move things around here, I'm going to have a cosine squared theta. Where'd my theta go? Cosine squared theta minus 2 cosine theta d theta and hopefully by now you're used to dealing with cosine squareds, right? What's our standard replacement for cosine squared? That's right. 1 plus cosine 2 theta all over 2, and then minus 2 cosine theta d theta. And don't mind, I'm going to bring this over here. So let's see, we're going to have a 1/2 theta, and then cosine 2 theta over 2. And then minus 2 plus 2 sine theta. And then from pi halves to 3 pi halves. And so notice that the 2 theta, right, is going to, this term will be gone with these inputs. So what are we going to have here? Let's see. So we've got a 3 pi fourths plus 2 times -1 minus pi fourths, or pi fourths plus 2 times 1. So let's see, this is -2 minus 2. So 3 pi fourths minus pi fourths. It's going to be pi halves. And then 2 times -1 is -2 plus 2 times 1 is 2. We're subtracting, so -4. We've got 1/2 of that. All right. Oh, and you know what? I'm sorry. I made a mistake here. This should be -2 sine theta. Sorry, guys. Which makes this -2 times -1. And then -2 times 1. So let's see. I'm gonna clean this up a little bit here. Sorry, guys. So let's see. We've got 3π4 minus π4, 2π4. So we'll have pi halves. Then I've got +2 minus a -2, which is 4. So what do I have here? π4 plus 2. All right. So there we go. I would advise going through and working through this again. And we'll certainly talk about it when we have our meeting as a class. Until then.